In this part, I will talk about the curvature estimate for stable minimal triple junction surfaces. These are the main topics in this part, including the definition of minimal triple junction surfaces, curvature estimate, and how to get the generalized Bernstein theorem from our curvature estimate. At first, we will need to clarify what is a triple junction surface in R3. Suppose we have three surfaces which we write it as sigma I with smooth boundary partial sigma I. We call the union of these three surfaces to be a triple junction surface if these surfaces share the same boundary in R3. That means partial sigma I will be isometric to a fixed one-dimensional submanifold of R3, which is written as gamma. We will use sigma gamma as a notation of the triple junction surface. Here are two examples of triple junction surfaces. The first one is a double bubble. The second one is a singular solution to the Plato problem when given two circles. These two examples show triple junction surfaces indeed have some physical meaning we can actually observe, and it can be used to generalize the concepts of minimal surfaces and constant mean curvature surfaces. This might be the one reason why we are interested in triple junction surface. Regarding triple junction surfaces, there are still a lot of results related to them. Here we list some of the related results. Li and Simon showed the regularity result near cylindrical tangent cone. After that, Brian Camel showed the higher regularity of minimal submanifold with the common boundary from C1 gamma regularity. If you look at this picture, basically, Simon's result tells us if we have a point with density 2/3 on a stationary varifold, then near this point, this varifold looks like a C1 gamma triple junction surface, and it is minimal in some sense. The Camel's result shows we can actually improve C1 gamma triple junction surface to be smooth, or even more. It is analytic if we only consider ambient space to be R3. Besides the minimal triple junction surface, there are also some people considering moving triple junction surface with its mean curvature, including Freer, Deppner, Garg. Recently, Schultz and White gave the regularity result of mean curvature flow with triple edge. Moreover, there are a lot of works on the network flow, which is a one-dimensional version of mean curvature flow with triple junction. Now, let me give the definition of minimal triple junction surfaces in R3. We say sigma gamma is a minimal triple junction surface if the mean curvature vector each sigma I vanishes identically for all I, and these three surfaces make a same angle with each other along gamma. This means that each piece of surfaces is a minimal surface with boundary. The angle condition here is just say the outer conormal tau I make an angle 2π/3 with each other. This angle condition equivalent to the condition that sum of tau I is a zero vector field along gamma. Still, like the definition of minimal surface, we have several equivalent definitions for minimal triple junction surface, and we will mention two of them. The first equivalent definition is sigma gamma is a minimal triple junction surface if and only if it is a critical point of an algebra function. Again, the equivalence can be found by using first variation formula. If you calculate the first variation of area, besides the integration related to mean curvature vector on surface, you can also get an extra integration along gamma related to outer conormal tau I here. So this expression equal to 0 for all x if and only if mean curvature vector vanishes on each surface sigma I and the sum of tau I equal to 0. This is exactly statement of our definition of minimal triple junction surfaces. The second equivalent definition is sigma gamma is a minimal triple junction surface if and only if the coordinate function xij is harmonic and sigma I and the sum of outer conormal derivative of coordinate function is zero along gamma. In the first part, we already know the mean curvature vector vanishes if and only if the coordinate function is harmonic on surface. Besides that, noting the partial derivative along gamma of position vector is just tau itself. Hence, the sum of outer conormal derivative of coordinate function equal to 0 is just equivalent to the sum of tau I is 0. So these two definitions are equivalent. Here are some examples of minimal triple junction surfaces. The first non-trivial example is a well-shaped catenoid. Here are two different kinds of Y catenoid. The left one is the standard Y catenoid. It has two catenoid ends and a disk in the middle. Then they make an angle at 2 pi over 3 along this circle. The right one is another kind of Y catenoid. It has 3 catenoid ends. You can choose a suitable scale and position of each catenoid end to make sure they intersect with each other at a fixed angle along this curve. Like the minimal surface case, we also have Y-shaped helicoid type minimal triple junction surfaces. The first one is the standard Y helicoid. Like the picture shows, we can make 3 copies of half helicoids and let them form the same angle along this vertical axis. The second one is the bent Y helicoid. We can use Bernoulli's formula to construct 3 copies of half-bent helicoid and make them form the same angle along this circle. This is an immersed example like the minimal surface case. Now let's define a distance function d on triple junction surface sigma gamma. We can define a distance function between 2 points by the infimum of all possible piecewise smooth curves drawn into these 2 points as we have written here. Note that even 2 points S, Y lie on the same piece of surface. The distance defined here might be different from original distance on this surface. With this distance, we can define the completeness of triple junction surfaces. Besides, we can define d gamma x to be the distance from any point x to gamma. We will use this distance to construct test function later on. We can also write TR gamma as a tubular neighborhood of gamma under distance d. Comparing with the result of minimal surface case, we can also get this proposition. There is no compact, complete minimal triple junction surface in R3. The proof for this proposition is just the application of usual maximal principle. Before starting the second variation formula, let's introduce some useful function spaces and fix some notation we will use later on. Still let sigma gamma to be our triple junction surface. When we say a function f on sigma, we always mean f has 3 components, f1, f2, f3, and each of them defined on sigma I. We do not require these functions agree with each other along gamma. Basically, you can think f as 3 independent functions defined on each sigma I. We say a function f on sigma is ck, where we use this notation here. If each fi is a ck function on sigma I, this is easy to understand since here we only mean we have 3 independent ck functions on sigma I respectively. From ck function space on sigma, we can define a subspace of it and call it as C1k sigma. We say a ck function f and sigma is in C1k sigma if fi and fj agree with each other along gamma. Here is an example of this function space. If we assume f is a ck function defined on R3, then the restriction of f and sigma will have three components. If we think it as three functions by restricting f on each sigma f, then fi equal to fg along gamma since they are thus restriction of f on gamma. Therefore, we know the restriction of f on sigma is a C1k function on sigma. From this example, you can see C1k function space is quite natural. Even the coordinate functions on sigma lie on this function space, but we still call it as C1k function space instead of ck function space since there are other kinds of function spaces important to us. We say a ck function on sigma is in C2k sigma if the sum of fi along gamma vanishes. Still, let's give an example of functions in this space. We choose V being a ck vector field in R3 and choose a normal vector field nu I on sigma I such that sum of nu I vanishes along gamma. This is possible if sigma gamma is a minimal triple junction surface and each sigma I is orientable and gamma is connected. Then the dot product V dot nu can be viewed as a function with three components. Each component is given by V dot nu I along gamma. By our choice of nu I, we know the sum of these components along gamma vanishes. This means V dot nu is a function in C2k sigma. From this example, you can see this function space is still a natural function space, especially in first and second variation formula. This is because if V is the vector field that's generating the variation of sigma, then the function V dot nu should appear in the first and second variation formula in some sense. For example, we can write the mean curvature vector h sigma I dot nu as h sigma V dot nu I. You can think C2k function space is a dual case of the C1k function space, since we will need second variation formula a lot later on. C2k function space is more important than C1k function space in this talk. Just like the ck space, we have three kinds of Sobolev space here. Again, we say a function in Sobolev space WKP if each component fi is a WKP function on sigma I. There is no restriction when talking about the values on boundary. Similarly, we say a WKP function f is a W1KP function if the components restricting on gamma agree with each other. Note here we need to assume k greater or equal to 1, since there is no meaning to talk about the restriction of LP function on boundary. For k greater or equal to 1, we should understand the restriction in the tree sense. On the other hand, we say a WKP function on sigma is a W2KP function if the sum of components vanishes along gamma in the tree sense. W212 space will be used a lot later on. After giving several function spaces, we will fix some integral notation and make several assumptions to make them easier to understand. From now on, when we talk about triple junction surface sigma gamma, we will always assume each sigma I is orientable and has only one boundary component. This means we will assume gamma is a connected curve in R3. In this case, we can choose a suitable normal vector field on each sigma I. We will choose nu I as a normal vector field on sigma I such that the sum of nu I vanishes along gamma. We will use nu, which has three components, to denote this kind of choice of nu I. Now, for any function f which has three components, including f in ck sigma and f in wkt sigma, When we talk about the integration of f on sigma, we always mean taking sum of each component fi integrated on sigma I. When we talk about the integration of f on gamma, we also mean taking sum of each fi restrict on gamma and integrate on gamma. Let's take first variation formula as an example. Using this notation, we can rewrite the first variation formula in this way. Note here, phi is a dot product of x and nu, which has three components, and we regard the h sigma as a tuple with three components h sigma I. We should understand x dot tau to be three functions defined on gamma and taking sum here, although tau is well defined only along gamma. After defining this notation, we can state the second variation formula and define the stability of minimal triple junction surfaces. Still, we use sigma gamma to be a minimal triple junction surface. We suppose sigma t is a variation of sigma with x is a variational vector field. Then the second derivative of area can be calculated by this formula. Here, phi is just a dot product of x and nu. H gamma here denotes the curvature vector of gamma in R3. Actually, the term of H gamma dot with tau I is just the geodesic curvature of gamma on surface sigma I. There is an X term which I have marked here. If you compare this formula with the second variation formula for Euro minimal surfaces, the calculation is essentially the same with the case of minimal surface, especially you familiar with the free boundary minimal surface. Note that this formula is still true in higher dimension case or even in general ambient manifold as long as you add back the rich curvature term and think H gamma as a mean curvature vector of gamma. Hence, we say sigma gamma is a stable minimal triple junction surface if the second derivative of area is not less than 0 for any suitable variation. As before, we can get the stability inequality. Note that since C2K functions are dense in W212 sigma, we can actually choose phi in W212. For this phi, we still have stability inequality listed here. Now we are ready to state the LP curvature estimate for stable minimal triple junction surfaces. Still, we assume sigma gamma is a stable minimal triple junction surface. Then for a test function phi in W12 and L infinity such that the function defined here belongs to W212. Then for P in this range, we have this following curvature estimate. Note that since we only assume gradient of phi in L2 space, we cannot apply Holder inequality or Young's inequality to separate these two terms. The different part with Euro LP estimate is we have the integration along gamma. If we add one more condition on phi, namely assume phi in W12P sigma, then we can apply Young's inequality above to get this version of LP estimate. This result lacks the Shou-Simon-Yao result we have stated in first part. Actually, in the later application, we can only make sure phi in W12, so we will only use the first version of LP estimate later on. You may notice that the significant difference between this LP estimate and the last LP estimate in the first part is we require P very close to 1 instead of P greater or equal to 2. This is necessary since we have a very bad term on boundary, the term right here. In the application of LP estimate, you cannot choose a suitable test function to control this term if P is large. In order to let this term sufficiently small, one possible method is choosing P very close to 1. This will lead to slightly different proof of LP estimate. Let's sketch the proof of LP estimate. Follow from the Euro minimal surface case. Let's change phi to phi times a to the power of p minus 1 in stability inequality. Keep in mind the condition for phi will change after this substitution. Here, the condition for phi is a phi such that phi times AP minus 1 in W12. After this substitution, we will have an X term coming from the boundary part of stability inequality. We have used the red box to mark these X terms comparing with the usual minimal surface case. Here, one may notice the term a to the power of 2p minus 4. Here, one may notice the term a to the power of 2p minus 4 and wonder if it is well defined since we assume p less than 2. Actually, it is indeed well defined. This is because each sigma I is a minimal surface, so the Gauss map is indeed an anti-holomorphic function from sigma I to sphere in R3. Hence, the norm of second fundamental form, which is the norm of differential of Gauss map, will have isolated zeros with finite order if sigma I is not flat. With these properties, we can verify all kinds of these terms are locally integrable, including the terms in the next several steps. If sigma I is indeed flat, we will view all of the integration contains a sigma I as 0. At the second step, we can multiply a to the power of 2p minus 4 phi squared to Simon's identity and integrate it. Here, Simon's inequality will become an identity when n equal to 3. Almost all of the terms are the same as before, except after doing integrate by parts of this term. We will get an x term on boundary here. Note that in this inequality, we do not need to impose any condition on phi since we do not use stability inequality here. At the third step, we can combine the last two inequalities. In this step, we need to use the p is near to 1. For example, assume p in the open interval from 1 to 5/4 is enough. As before, we can cancel out a lot of integrations on sigma, but still two boundary terms appear. In the fourth step, we can change phi to psi of phi times the phi to the power of p. Then the condition for phi will change to the one in our statement of theorem, the condition listed here. After substitution, we will immediately get the first result in our theorem. If in addition we assume phi in W1 to p sigma, then we can apply Young's inequality to separate these two terms. Here we also need p is slightly greater than 1 since we need to left-hand side can absorb the x term after separating terms. After that, we can get second LP estimate formula with some extra terms on boundary. With LP curvature estimate in hand, we can solve the generalized Bernstein theorem use this curvature estimate. Still, we need extra conditions on the triple boundary gamma to get this theorem. In the first theorem, we will assume gamma is compact. More precisely, let sigma gamma be a complete stable minimal triple junction surface. We also assume sigma has quadratic area growth. This means that we can find C such that area of B RP over R squared can be bounded by C for all R and all P in sigma. In addition, we need gamma to be compact. This means gamma is a closed curve in R3. Then we can get each sigma I is flat. Note that if all of sigma I is flat, then gamma should be a straight line and gamma cannot be compact. So this theorem indeed tells us there is no complete stable minimal triple junction surface with quadratic area growth and gamma compact. The second theorem requires gamma to be a straight line. We assume the same condition on sigma with above, except assume gamma to be a straight line. Then we have the same theorem that each sigma I should be flat. From this theorem, we know the only possible minimal triple junction surface that meets these conditions are three half planes from a well-shaped cylinder, just like the image sketched here. Since the case of gamma being straight is easy to prove, since all of the unfavorable terms integrated on boundary gamma vanishes, so you can view it like the case of Euro minimal surface. But for a case of gamma being compact, we need extra words to get all things can go through. Now let's start the proof. We assume none of sigma I is flat at first. We write our LP estimate in 3 terms as written here. Next, we need to choose a suitable test function. Here we cannot choose a Euro test function that be constant in a large ball, since at least we need phi to satisfy the complex condition along gamma. In this proof, let's choose 3 non-zero constants. The sum of them equal to 0. Let rho r be the standard cutoff function that's supported in T2R gamma equal to 1 in TR gamma with bounded gradient by C over R. Define several auxiliary functions Gi to be the product of all norms of A sigma j except A sigma I. For example, G1 equal to norm of A sigma 2 times norm of A sigma 3. Although Gi is only well-defined on gamma, we can extend Gi to be a smooth positive function on sigma I except several finite order zeros on gamma. The precise statement of extension will be defined in my paper. To save time, we just assume we can get a well-defined Gi on sigma I. Now we can use Gi to construct test function using this formula. The important properties about this phi is when P in gamma, rho Rp will equal to rho 1T and equal to 1 by the choice of rho R. So you will find out this quantity here. Maybe I just write it components out, has this form. So this function in W2, 1, 2, sigma. On the other hand, if P in TR gamma, but P is not in T2 gamma, then we only have this term left. So phi I is a fixed constant in this region. This part is like the Euro test function in minimal surface case. Now let's estimate these 3 terms one by one. For the third term, we need to make sure it is positive. Note that we can write out this term without cutoff function since it is a gamma. If this integration is less than 0, we can adjust the Ci to make sure it is non-negative. Actually, there are a lot of ways to choose suitable Ci and they are elementary. For example, you can change C to C2 minus C3, C3 minus C1, C1 minus C2 to change the sign of third term. For the second term here, as we mentioned before, we need to choose P close to 1 enough to make sure this integration is small enough. This is the reason why our method can only apply to the case of minimum triple junction surface, not the higher dimension. The trick part is the first term. As we have explained earlier, we want to apply Young's inequality to separate these 2 terms. But based on our choice of phi, gradient phi only belongs to L2 here is 0. So one possible method is just divide the integration to 3 regions. The first region contains small balls near 0 of G, which we write it as S, the singular part of G. Since gamma is compact and G has only isolated 0, we know there are finite balls here. The second region is the region near gamma without 0. The third is the region far from gamma. Note that phi is locally constant in the region TR gamma, but out of T2 gamma, so we can omit the integration on this region. For the integration on first region, we can choose S small enough to make the integration small as we want. Then for the integration on second region, we need to choose P close to 1 enough to make it small. This is because G is strictly greater than 0 in this region, so phi converges to C uniformly in this region as P goes to 1. Then the integration will converge to 0. Hence, we can choose p close to 1 to make sure the integration is sufficiently small. From now on, we can fix p greater than 1. For the last region, it can be controlled by c r squared over r to the 2p. Using quadratic area growth condition, by choosing r large enough, we can still make sure this integration is small. Combining these estimates here, we can conclude that A should vanish. This will contradict that all of sigma I is non-flat. The case we left is sum of sigma I is flat. Note, since we assume gamma is compact, there are at most one of sigma I can be flat. Suppose sigma 3 is flat. In this case, we need to choose the phi 3 identically equal to 0. Here is a geometric way to think about it. Any plane is stable, so you do not want to move it since it will always put back terms in the second variation. In this case, you have no choice of C3 but 0. So basically, C1 and C2 are all fixed up to a scaling. So we cannot adjust the sign of third term by choosing suitable C. For this case, we need the following lemma due to Brian White. This lemma tells us the geodesic curvature of boundary can be controlled by interior curvature. So if we choose phi in this way, then we have the following formula. Note that there are two approximation terms since as p goes to 1, they will become closer. So we can control the third integration by this integration by choosing p close to 1. After that, we can follow steps in the previous proof. At last, let's mention a bit the relation between capillary minimal surface and minimal triple junction surfaces. The statement here is not formal, since for capillary surface we might need more space to give the precise definition. Note that if sigma 3 is flat, then sigma 1 and sigma 2 are symmetric across the plane that sigma 3 is located. Moreover, sigma 1 and sigma 2 all have a fixed angle 2 pi over 3 with this plane. So we can think sigma 1 as a capillary minimal surface. If we define the suitable energy for this capillary minimal surface and define the stability for it, then we have this corollary. That is, you cannot find a suitable complete minimal surface that boundary is in a plane and compact, and sigma has quadratic area growth and have a fixed angle pi over 3 with this plane. Here is a remark for this corollary. Recently, Han Hong and Artur Saturnino gave more precise result for capillary surface. They use different methods in the proof and they can remove a lot of constraints in above corollary. As I have noticed, Han Hong will do a presentation about their result, so you can take a look at his talk. Thank you for your attention. If you have further questions, please come to QA session. I'm looking forward to seeing you there.